All right, everybody, this is lecture 34, and I'm pre-recording this today. As I posted on Teams, my neighborhood is, the only way to access it is by a single point of entry, a bridge that is an overpass over 64. And with the tornado and the storm today, I'm kind of stuck in my neighborhood. Just to give you sort of a view of what it looks like in my neighborhood. This is the sign that fell over the road, and then I have a side view over here. It's an absolute mess. So yeah, I am just sort of here at home right now, and I actually went out to the site just now, and the repair crews said that they would have it repaired. They think they'll have it repaired this evening, or get at least have a lane open. But I know we're also supposed to get hit again with some more poor weather. So I thought, let's just go ahead and pre-record this lecture, and we'll see what happens. Regardless, I'm going to count everybody present for today, whether you can make it or not, and then we will get this straightforward. And I've got the YouTube playlist up to date as well. I am going to have a homework assignment for this lecture, and it's going to be due Friday. And I want to go ahead and get right into it because I want to value your time. So today what we're going to do is begin our discussion of discretely braced beams. Specifically, we're going to talk, we're actually not going to get into the analysis and design of the beams yet. We're going to sort of talk about the underlying background and the theory. We're going to do a little bit of math, a little bit of Diffie-Q today. Don't worry, you won't have to do that on an exam or anything, but I want to show you the derivation for the solution for LTB and then show you a problem with it. And so today's lecture is really going to be focused on how we address that problem, and we address it with what's called a moment gradient modifier, and the term is called CB. And so with that, let's go ahead and jump right in. Let me pull up the slides here. Let me close the slideshow here, pull these slides up. Okay. So like I said, the purpose of today's lecture is to discuss the moment gradient modifier, but it's going to take us a little while to understand what that is and what the purpose of it is in the context of steel beam design. So to begin, I want to say a few words, and let me go on here. Let me make my camera a little bit smaller, just so y'all can see the slide. The slide's more important than me. Okay, I want to say here a couple things. We are going to have some calculus and some differential equations showing up here in a little bit. And I want to be clear, we're not going to have to do any of this calculus on any homework or any exams. Not worried about that. It's really just to provide background. And it's going to be a little bit heavy, at least heavier than the solution for columns. So the big thing that I want to sort of put in your head as a thought is the following two math problems I have here on the screen. Okay, so I have here on the screen two derivatives. Okay, and I'm using this just as a means of explaining what I'm going to talk about later. But let's just take these two derivatives one at a time. So the first derivative is on the left. I have the derivative of 5 times the sine of x. Okay, and the 5 is bolded, or I made it red and kind of bolded because I really want to talk about how we treat that. So in Calc 1, or in basic differentiation, when you take a derivative, you can treat that 5 as a constant, and so rules of differentiation say you can factor a constant out, and then you're just taking the derivative of the sine, which is the cosine. So the answer to the first derivative is just 5 times the cosine of x. So then the question becomes, can you do that for the second derivative? Can you just say, well, then it's x cubed times the cosine of x? No, you cannot, okay? Because x cubed is a variable, it makes things trickier. Now, for this derivative, you learn how to do this derivative in Calc 1. It's pretty straightforward. You just apply the product rule and so on and so forth. But the point is those coefficients are handled differently when one is a constant versus one is a variable. And it's a lot easier to deal with constants when we're talking about calculus and differential equations because we can just sort of factor them out of our expressions. And we're going to find that we really want to do that for our solution for lateral torsional buckling, but there's one term that's a problem, okay, and we'll see what happens with that here in a bit. Okay, so back to bracing and back to this term LB. So we talked about it a little bit ago, but I said we really weren't going to use it directly until we get to discretely braced beams. Well, now we're going to actually start discussing it. Okay, so I have a beam, and remember there is a difference between the beam's length and its unbraced length. its length is, literally how long it is. In the case of a simply supported beam, it's just, L from support to support, but LB is the distance between braces. So we could very well have a situation where we have a 60-foot long beam, but it has braces every 20 feet. And so there's a difference between the length and this term LB. Now, up until now, we've been dealing with situations where LB was 0. So we had an infinite number of braces, or a continuously braced beam. And whenever you have a continuously braced beam, you just say that the nominal moment capacity is MP. I should say there actually are a couple scenarios where that's not the case. We'll talk about local buckling later, but for the sake of now, let's just assume that MN equals MP. Now what we're going to do is look at discretely braced beams where LB has a value where it's greater than 0. And so the question is, what is the capacity if you have a discretely braced beam? And that's actually what our focus is now. Now, what happens is when a W shape is being bent, there is a stability problem, okay? The top of the beam, let's say in this scenario here, we have a simply supported beam subjected to a load up top. So the top is in compression, the bottom is in tension. There's a little bit of a challenge that the beam has to resolve. And what's going on is part of the beam is in compression, and the elements that are in compression, they want to buckle. But part of the beam is in tension, and the parts in tension don't really want to buckle. And the only way that the beam knows how to deal with this is if we have this cross section, the only way the beam knows how to deal with it is to sort of kick out and twist. And so that we have a name for that phenomenon. We call it lateral torsional buckling, okay? And so this is an image, sort of a conceptual view of what LTB looks like. And you can see sort of the section kind of rolling over and twisting laterally under this applied load. And that happens when the braces are discrete, when they're not continuous, okay? I have a couple real world examples. This image here on the right is from a bridge that was in Canada in 2015. I think I showed you all this a few lectures ago, but you can see that as they're placing it, the beam is discretely braced and then the beam wants to buckle. You can also see that the, from this, it's not just the beam that's failing, it's the braces themselves. The braces are seeing a lot of force. They got to prevent the beam from moving left to right. And so the braces take on a lot of load to prevent that from happening. And so you can see we have brace failure and beam failure here. This image over here on the left is a screen capture from a video. I put the link of the video here in the slide, but this is actually a lab test where you can see they're actually loading the beam, and you can watch it LTB. You can watch it sort of roll over as the test progresses. So it's worth checking out. I might put that in the playlist. Okay, now we're gonna do a little bit of math, so let's get ready for it. Okay. So ultimately what we want to do is derive a solution for the moment capacity. So what we want to do is we want to say, okay, here's a beam, how much moment can it withstand before it buckles, okay? And we said that the beam wants to kick out and twist, okay? So I want to talk about twisting, okay? And I want to talk about the math associated with that. Now everybody in here has had mechanics of materials or mechanics of deformable bodies, engineering 216. And one of the classical problems in Engineering 216 is how to deal with torsion, how to deal with an element that's being twisted, okay? Now, in that class, you primarily deal with sections that are circular, so like solid shafts, pipes, etc. The reason is that when you twist a section that is circular, it deforms by rotating. And it's really all it does, okay? So really the goal in mechanics from that perspective is to relate the amount of torsion to the angle of twist, okay? And so we can relate that. We actually have a differential equation for that. We can say that the torsion is equal to the rate of twist, the first derivative of that angle, times Gj. And Gj is just the torsional stiffness. G is a material property. It's sort of like Young's modulus. It's the shear modulus. And J is the, in the case of a circular cross-section, is just the polar moment of inertia. Now that's what happens with a circular section. And in Engineering 216, you primarily focus on circular sections, okay? Because non-circular sections don't just rotate. They rotate. I mean, if you take a section and twist it, it will turn. But non-circular sections do something a little different. They deform in a different way, which what we call warping, okay? So whenever you twist a circular section, it stays flat after it's twisted. So it's, if this was the surface, let's say this was the surface of the pipe, when you twist it, it still remains flat. But that doesn't happen for things like ice shapes, which aren't circular. Not only do they rotate, but they warp. And you can see in this image down below, the flanges, they actually sort of deform in and out of plane. Okay, it doesn't stay flat after it's twisted. So whenever you have a section that is non-circular, you have to add a term to the differential equation. So the torsion is not just GJ times the rate of twist, it's GJ times the rate of twist minus this other term here. And the minus just comes from sign conventions and mechanics and whatnot. But we basically say that the torsion equals the pure torsion response minus this warping torsion response. And the warping torsion equals the Young's modulus times this warping constant. And again, you can grab your steel manual right here and look up warping constants for all of your W shapes. If you want to talk about how to compute those, we can talk about that. It's a little bit involved, but well, not really. I mean, there's some closed form formulas for it, but the process is a little out there. But we take E times the warping constant times the third derivative of twist. So with pure torsion, it's the first derivative. With warping torsion, it's the third derivative. The reason it's the third derivative is because we look at that flange and we see the flange is kind of shearing. And so like the second derivative is related to moment, the third derivative is related to shear. So that's why it's in that fashion. Okay. So I want to sort of, like I said, the derivation is kind of involved. So to put it in perspective, like when we were looking at column buckling, we only had one differential equation to solve. We said that the second derivative of deflection plus P over EI times Y equals 0. And we solved this differential equation. We solved this differential equation right here in order to get this term. Like that was the solution. Like that's the buckling load, right? Now we took this buckling load and we modified it, but that's the solution, okay? So we only have one differential equation to get this. But with beam buckling, we have three differential equations. So remember what's going on. During buckling, the beam is kicking out and it's twisting. So there's a lateral deflection, there's a twisting, but then also we're just bending the beam, right? So there's the vertical deflection as well. So we have the differential equation for vertical deflection, which this is just beam deflection. This is just the second derivative of deflection is m over EI. And I'm using V for vertical deflection, and I'm using this term U for lateral deflection. So the lateral deflection is m over EI, but then there's some trig in there. And then we have this this torsion equation, which we just saw on the previous slide. So these two are really just, beam deflection with a little bit of trig, and then this is the one we just saw. So what you have to do is you have to combine these, and then, basically you're substituting one into another to get a single differential equation. And so it's a little bit more involved. I'm happy to provide a detailed derivation if you'd like, but it's a little bit involved. Now, when it's all said and done, you get the following differential equation right here. This is a fourth order differential equation. So what I've got here is this box and this box right here are the same box. This is just written sort of in shorthand down below. So we have essentially a fourth order differential equation. So if you want, you can think of it as something like a constant times y to the fourth derivative plus a constant times y times the second derivative plus a constant times y equals 0. So that's kind of the form for the differential equation, only instead of y, I'm using phi because the variable in this case is not a deflection, it's a rate of twist. Okay, so that is a pretty involved differential equation. Okay, long story short, we can produce a solution to this differential equation, and the solution to this differential equation is actually this right here. Again, I'm happy to provide a more detailed solution, but just suffice it to say that this solution works. Now, there is a problem with this derivation. There's an issue with it, okay? The issue is it goes back to that very first slide I showed you about the derivatives, okay? Remember those derivatives at the beginning of the lecture where we could factor out the 5, but we couldn't factor out the x cubed, okay? Here's the issue with this solution. And again, you don't really need to go into the weeds of all the differential equation solution and all that. You don't really need to get into that. You just kind of need to understand this idea, okay? Now, this is the differential equation that we solved, okay, to get that answer. Okay, so the idea is that we solve this differential equation to get this yellow answer down here. Okay, so the idea is that that yellow answer satisfies this differential equation. That works, but there's a problem. Okay, let's look at this differential equation. Okay, so let's look at all of these coefficients and let's see whether or not we can treat them as constants. Okay, so let's go here. Can we treat E as a constant? Well, for steel, yes, E is 29,000 KSI, okay? And the same thing is going to be true for G, because G is also a material constant. For steel, it's about 11,200 KSI. So that's a constant as well, okay? What about CW or J or IY? Well, for any rolled shape, yes, those are constants. I mean, just open up table 1-1, just find a W shape, and you'll see that IY, J, CW, these are all, constants for any shape. It's sort of like a section property. It's like saying the depth of the section. That's a constant, so you can factor that out. The problem is moment, okay? The problem is this term right here, okay? So basically, when we solve this differential equation, we treat everything like a constant, and it makes the solution of M really simple, okay? But the problem is that that's false for most real-world scenarios. I mean, let's go back to last semester. Let's go back to structural analysis. How many moment diagrams did we ever see that looked like this? Not really. Most of our moment diagrams were all over the place. I mean, we had moment diagrams that, looked like this and looked like all sorts of, strange shapes for moment diagrams. But we never really had a moment diagram very often that was just straight. That was pretty rare, okay? Moment is usually a variable, okay? So the idea is that we have this really awesome, simple plug and chug expression for the solution of a differential equation, but that solution assumes that moment is a constant, and moment isn't. Moment has gradient. Moment changes. So what do? We introduce what's called a moment gradient modifier. So the name for this is CB. And so what is CB? CB is a means of adjusting our solution for LTB to account for the fact that moment changes. And that's really what C sub B is. Okay, so let's talk a little bit about C sub B. So C sub B, we call this a moment gradient modifier. One way of thinking about C sub B is that it's kind of like a slope of the moment diagram. That's not really the case, but it kind of is. The more moment changes, the more moment changes, the chances are that CB is higher. And I say chances because there's some caveats for how you compute it, which let's get into that right now. Okay, so the way that CB works is you take a beam and you split it up into a series of unbraced segments. So if we're looking at this beam on the slide, this beam only has one unbraced segment from brace to brace. And for each of those segments, for each of those unbraced segments, there's going to be a CB. So if it was an 80-foot beam and there were braces every 20 feet, there'd be 4 CB values. One for this segment, one for this segment, one for this segment, one for this segment. Okay. For each segment, what you do is you split it up into quarter points. Okay, so if it's a 20-foot distance between braces, you calculate moments at 5 foot, at 10 foot, at 15 feet. And you letter those MA, MB, and MC. Okay, those are what we call the quarter point moments. Now, it doesn't matter if you go left or right, because in the expression, here's the equation for C sub B, they're treated the same way. So you could go MA, MB, MC, or MA, MB, MC. It doesn't matter. But essentially, MA, MB, and MC are in between the braces at quarter points. M max is the absolute maximum moment within the segment. So M max could be the moment on this end of the brace or this end of the unbraced segment. It could be on this end of the unbraced segment. It could be equal to one of these quarter point moments. It could be away from these quarter point moments. It doesn't matter. Okay, you just take the absolute maximum moment. So, for example, for this beam, this is a simply supported beam subjected to a uniformly distributed load. So in this case, MA, MB, and MC are labeled, and then M max is actually equal to MB because the maximum moment is in the middle of the beam, and that's also where MB is. Okay. Now, the big thing about these moments is two things. You always use factored moments, so don't use like an M dead and an M live. Just use factored moments, factored loads, factored moments, and all of the moments are taken as absolute values. So the moment diagram can go up and down and up and down. It doesn't matter. Use positive values across the board. Okay. So to explain CB, I want to give you an example, and that's what I kind of want to focus on for the rest of the lecture. So I have a overhanging beam with some distributed load present on it, and I've already had and given you the reactions, and I want to determine CB values for each of these segments. So each of these segments is going to have an unbraced, or each of these segments is going to have a CB. So there's going to be 3 CB values at the end of this problem. Now, a couple things. I have given you the reactions and I've given you the shear and moment diagrams on some later slides. But another thing worth mentioning is that this is a factored load. It's not a dead load and a live load. I've gone ahead and factored everything. So all the loads are factored so we can use them directly. So here's the shear diagram, and you can see. Here's what would happen. We would go up, go down, go up, go back down. So we can see where the shear diagram is coming from. I've integrated the shear diagram and then gone to plotting the moment diagram. One thing worth mentioning, so if you're looking here at the shear diagram, the absolute worst case magnitude shear is actually this value right here. So if I was in shear design mode, I would just ensure that my beam has enough capacity to withstand a shear of this. Now, for most building design problems, that's okay. In bridges, we might have to handle shear a little bit more differently, maybe more akin to how you handle it in reinforced concrete design. But just for the sake of discussion, in building design, won't really be too big of a deal, unless it's a transfer girder or something like that. Okay, here's the moment diagram, and I've sort of plotted that out accordingly. Actually, let me go ahead and pull the notebook out because I sort of lined everything up here in the notebook. So if you look here, you can see like I plotted the beam and the shear and the moment diagram kind of on top of one another the way that you would in structural analysis. I had to kind of stretch the beam image a little bit so that it would all kind of line up, but I tried to do it as equitably as trying to line that up as much as you can. So you can kind of see, for example, that this location of 0 shear sort of corresponds to where that max moment is. Again, I probably could have formatted that a little better, but you got to kind of get the idea. Okay, so what we're going to do is we're going to compute CB values for each of these segments. And so I'm going to treat this like a straight up structural analysis problem. So if we think about this from a structural analysis perspective, let's sort of go back to a very important topic in structural analysis, and this is moment functions. Okay, so here's the beam, okay, and I have a support condition here, and I've got a distributed load about like this. So a question worth asking is how many moment functions are required to fully define the moment diagram for this beam? And the answer is 2. And I mean, you can see that kind of right here because this is a single parabola right there, and then this is a parabola. There's only 2 mathematical functions that define the moment diagram, okay? So we're only going to need to cut 2 sections. Now, what I'm going to do is I'm going to cut a section here and look this way, and then I'm going to cut a section here and then look this way. Okay, remember, I sort of like to look towards the free end. It makes the math a little easier. And then on section 1, I'm looking towards that left support because there's less going on. In this part where you're trying to derive the moment functions, you can ignore these braces, okay? Because these braces do not affect the shear and moment diagram in the slightest. Really, these braces are just points of interest for you as the analyst, but from a moment diagram or shear diagram standpoint, don't affect anything at all. Okay, so with that, let's go ahead and derive some moment functions here. So let's go ahead and do this. So moment functions. Okay, so for section 1.1, let's see. For section 1.1, so let me go back up here. So we're cutting a section looking to the left. So we're gonna have a problem that looks something about like this. Then we're gonna have a distributed load like that. Then we have a support condition like this. So that's the section cut. That's section 1-1. Okay, and at this cut, we're going to have an unknown shear and an unknown moment. Let's call them shear 1 and M1. Now, I'm actually not going to derive the shear function. I don't really care. I don't need it for this problem, but I just wanted to throw that out there. Okay, so here's my function. All right, so what do I know about this right here? I know that the reaction right here is 22.5 kips, and I know that this is 2 kips per foot. Let's go ahead and lower this a little bit. Let's get that out of the way so that it's just a little bit out of the way. Okay, all right. So now we need to derive a moment function, okay? And what I'm going to do is, remember, when I have a distributed load, I'm going to collapse that into a single point load. And the point load, now what is the magnitude of that point load? Well, it depends on how long this section is. And since I'm cutting a section at an arbitrary location, I'm going to call this distance x. Okay, so this magnitude is 2x times, and then this moment arm right here is going to be x over 2, because it's a rectangle. Like, that load is just a rectangle, so it's just right in the middle. So if I sum moments at the cut, I can do better with that. All right. Okay. My dog is here asleep on the floor. No. All right. So I've got 22.5 times x. And I'm going to, since everything's in a consistent unit system, I'm just going to not worry about the units over here on the math. And then going this way, I've got 2x times x over 2. Then I also have M1. Okay? So I've got 22.5x equals M1 plus x squared. So M1 is 22.5x minus x squared. Now, this is going to be valid for this left part of the beam. So from x equals 0 all the way to x equals 30. Okay? And you're going to see, where this comes from here in a sec. So we'll put 0 to 30 right there. Okay, so let's go ahead and circle that as a solution. Okay, and I'm going to write that down on my little notepad here just so I have that. Okay, there we go. So here's this section. Now let's do section 2-2. Section 2-2 is a lot easier, okay? Section 2-2 is a lot easier because section 2-2, we're, if you go back up here, we're cutting a section and then looking to the right, okay? So really all we have for section 2-2 is this. So we'll cut that right there. This is 2 kips per foot. This is, again, x right here. In structural analysis, we called that like x1 and x2. But I think for here, we understand enough that the context will be fine. Here's our shear. Here's our moment. I'll do M1 and M2 here since they actually are different functions. And so if I... again, collapse 2x times a moment arm of x over 2. Let me move that down a little bit again. I don't really want to squunch that. So summing moments at 0. So this one's got a much fewer expressions because I've got M2. What happened there? Let's try that again. M2. And then I have 2x times x over 2. So this one is just m2 plus x squared is 0, or m2 is minus x squared. Now this is going to be valid from x equals 0 to x equals 15 because, and again, my apologies if I'm scrolling a good bit here, but we're talking about this function right there, and in this case, this is x equals 0, x equals 1, x equals 2, x equals 3, and this right here is x equals 15 because we're sort of defining x going that way. So that's why it's only valid from x equals 0 to x equals 15. Okay. Okay. Hold on. Let's see if I can get rid of all that. Okay. All right. So we have our two moment expressions, but that really doesn't help how to solve for CB. Okay. So I'm going to cheat a little bit. I'm going to copy this down here. And I'm going to make this a little smaller because I just need kind of an image here for reference. Okay, so hold on. I think my computer's freezing up. Give me 1 second. Apologies, I think my computer was freezing up there for a second. Okay. So what we're going to do here is I'm just using this sort of as a reference, okay? So what we're going to do is compute our moment gradient modifiers. Okay, and the way this is going to work is here's the beam, and I've got the moment diagram indicated right here. Now, the way this beam is configured, so I'll draw the beam sort of like right here. Here's the beam, and then there's a support condition right here. There's a support condition right here. But braces, so braces are right here, right here, right here, and right here. Okay, the braces are every 15 feet. So what I'm going to do is I'm going to take my moment diagram and I'm going to look at each of these segments sort of independently. So let's look at, this segment first. Let's look at this segment. Okay, so this segment is from here to here. So the only thing I care about for this segment are the moments inside there. Okay, so what I'm going to do is I'm going to determine moments at the quarter points. So I want to know the moment right there, the moment right there, and the moment right here. Okay, I want to know those moments right there. Okay, let's just do those. All right, so this segment is 15 foot long. So I'll say note 15 times, here, I'll do it like this. So 15 over 4 is 3.75, I think. Yeah, make sure I'm, 3.75. So what we're going to do is we're going to calculate these quarter point moments. So we're going to call it MA, MB, MC. Okay, so MA, MB, and MC. So remember the expression that we're going to use is M1, which is 22.5x minus x squared. That's the mathematical expression that we're using. Okay, so if we want to calculate MA, it's just M1 at x equals 3.75 feet, or 22.5 times 3.75 minus 3.75 squared, which equals, let's see, so 22.5 okay, so I'm getting 70.31. Okay, and that kind of lines up with what I'm seeing here on this plot. Okay, so MB is going to be M1 at x equals, so that's going to be 7.5 feet, which is, give me 1 second. 112.5. And then MC is going to be M1 at X equals 11.25. Which is going to be 126.56. And these are all in foot kips, so maybe I'll put the units right here. One of the things about CB problems is that if everything's in a consistent unit system, then the units are pretty straightforward. Okay, so that's MA and MB and MC. What about Mmax? Well, Mmax is the largest moment within this entire segment. So what you need to do is basically look at this entire curve from end to end and go, where is the biggest moment in this entire curve? Now, I'll go ahead and tell you for this curve, Mmax is actually equal to MC. Okay, and the reason why is, I'm going to scroll a little bit. So if you go up here to the shear and the moment diagram, so here's the shear diagram and the moment diagram. So if what happens here? So we go up 22.5 kips, so shear diagram tells us to go up. Then we slope down, right? The slope here is 2 kips per foot, because 2 kips per foot is equal to the load. And we cross 0 at 11.25 feet. And 11.25 feet happen to be where we calculated MC right here. And if I erase this, I mean, if I erase right here, you can see here on the diagram right here, that little dot there, I was showing that dot that's the maximum moment within that segment. Okay, so Mmax happens to be MC, which is 126.56. So in order to calculate CB for this segment, it's really easy. I've got MA, MB, MC, Mmax. Once you have those terms, CB is very plug and chug. So CB is the following. So it's a big old fraction. On the bottom of that fraction is 2.5 Mmax plus 3 MA plus 4 MB plus 3 MC. That's all under 12.5 Mmax. Again, it's really, really easy, really plug and chug. Notice what happens if all the moments are equal. Like if all these terms are equal, Mmax, MA, MB, MC, if they're all equal, then you have 12.5 on the top and then you have 12.5 on the bottom. So it actually comes out to be 1. So if you had constant moment, if all the moments were equal, then CB would be 1. And it would not affect your differential equation solution. So again, it's consistent there as well. So we plug and chug. So we get a big old fraction here on the bottom. Okay, so let's see what I got here. So let's do a big old fraction. Okay, let's make sure I got all my inputs right. Okay, I'm getting that CB is 1.166. Okay, let me check that just one way. Yep. Okay, that's what I'm getting. 1.166. Okay, so for this segment right here, so if I scroll back up here, this segment has a CB of 1.166, okay? And so the next thing to do is to just keep on trucking, okay? So now we're going to get a CB for this segment. Okay, so how do we get a CB for that segment? Well, we do the same thing. We're going to compute an MA, an MB, an MC, and an Mmax. Okay, so first off, just to indicate, okay, here's MA. Now, here's MB, okay? Here is MC, so this is MA, okay? And so how are we going to do that? We're just going to keep using the same moment expression. We're just going to plug in different distances of x. So instead of 3.75, 7.5, 11.25, and 15, we're just going to keep going. Now, what is Mmax within this segment? This is a really good question, okay? Now, some of you might be tempted to say it's one of the MA, MB, MCs. That's not correct, okay? Because there's clearly higher moments on the ends. But then the question becomes, do I use this moment right here, or do I use this moment right here? And the answer is to use the one at the bottom. Remember, when we plug and chug into the CB expression, we use absolute values. Mmax is the biggest moment on the section, period, from an absolute value standpoint. And I can just look at this graph and tell you that that moment up top is smaller than the one down at the bottom. The one down at the bottom is going to be pretty big. Okay, so Mmax is going to be right there. All right, so maybe what I'll do, here's what I'll do is, let me rearrange these calculations a little bit. Put that over there. This is certainly something you cannot do on a whiteboard. Okay. And so what we'll do is we'll take all these right here, bring them down, and because I want to make this kind of neat. I want to make this followable. Wish I had done this earlier. There's a method to the madness, I promise. There we go. That's what I like. Okay, so squunch it up together. Okay, so these are going to be the moments, or the... So this is segment 1, so we'll call this the first segment over here to the left. Now let's look at segment 2. So we're still using the same moment expression. Okay, so we have MA, MB, MC, and Mmax. So maybe what I'll do is, just to make sure we remember where this is coming from, put that over there. Let's just make sure we have it sort of at reference, okay? Okay, just to clean that up a little bit. Okay, so this is the same segment that we're doing, but instead of doing 3.75, 7.5, 11.15, we're just going to keep on going. So this is going to be M1 at X equals like 18.75. So, and then this one's going to be M1 at X equals 22.5. This is going to be M1 at X equals 26.25. This is going to be M1, in this case, at X equals 30. Okay, because again, from our moment diagram, we know that the biggest moment is on that far end. So I'm just going to plug and chug into this expression. Okay, so I'm just going to use my substitution feature here. So this one is 70.31. Well, 70.31. This one is 0. Ooh, this is actually 0. Okay. Now, does that make sense? Does it make sense that it's 0? Well, look right here. Where did we get MB? MB is right there. It's 0. So I thought it might be like just based on the Excel plot, it might be like a really small value. But yeah, it's 0. So what about 26.25? This is negative 98.44. And this is negative 225. So these are my 4 values. Now, the thing is, though, this is really important. Use positive, how about this? Let's start out this. Use absolute values. Whenever you're computing CB, just use absolute values. Don't use positives and negatives. Okay. So CB in this case is. So let's go ahead and let's just do it formally. Okay, so let me scroll up a little bit so I got a little more room to write. So 2.5 times, now M max when we computed it is negative 225, but we put a positive value here, plus 3 MA, so 3 times 70.31, plus 4 times 0, plus 3 times 98.44. No negatives, positive values only. Okay. All right, so what do we get here? Let's see. Okay. I'm getting 2.632. I want to verify that. I don't have my notebook with me because it's in the office and I can't get to the office. Yep. Okay, 2.632. So this right here is 2.632. And then we'll do the last one here. Okay. So with the last one, we're going to have MA, MB, MC. And then M max is going to be here. Now we're going to use a different expression. We're going to use the M2. Okay. Now M2 defines X as going this way. So actually what I'm going to do is, because I think it might be easier from a bookkeeping perspective, I'm going to flip these. I'm going to say that this is MA and this is MC. Remember, it doesn't matter if you go left to right or right to left. You're going to get the same answer. Okay. So segment 3. So we're using M2, which was just minus x squared, right? That's what we got. Yep, minus x squared. And we're going to say MA, MB, MC. And this is just going to be M2. Okay, And again, I'm just going to chug it out. I know we're getting close on time. I want to try and keep this video as short as possible. So let's see. So this is negative 14. Negative 14, not 4. And then this comes out to negative 225, which is a nice little check because when we use the M1 function, we got the same value at the same point. So these are our moments. And again, use absolute values. Although for this particular segment, I don't think it really matters that much because the negatives should cancel since all the values are negative. But again, just use positive values. So... And I'm not going to regurgitate the equation because I think you know it at this point. So all right. Okay, so when I chug this out, I get 2.326. Okay, and so there you go. CB is 2.326. Okay, and again, they're not exactly this, but you can kind of think of them as like the slopes of these moment diagrams, even though that's not really the case. But there you go. Here's our answers. So CB is 1.166. CB is 2. What did we get? 632. And CB is 2.326. So we'll call this seg 1, seg 2, seg 3. There's our answer. Okay. Now, the only thing, I know we're cutting it close. I know we're getting kind of short. So I do want to mention one thing. I'm going to try and give you a little bit of a hint on this homework assignment. So this is the homework assignment right here. And so I want you to do this problem, okay? So I'm giving you a simply supported beam with a uniformly distributed load, and it's the same problem. It's the same beam, but I want you to do it two different ways. I want you to do it one way, assuming that there's just bracing at the ends. Then I want you to do it another way, assuming there's bracing at the ends and bracing at midspan. So the first problem, there's only one CB term, but the second problem, there's two CB values. But the problem, the structure is symmetric, so you're going to get the same CB values on either side. But the real hint, the two hints, is that number one, you can use statics or you can use table 323 to compute the M values, because you don't need to like cut sections and do any of that stuff for this problem. Because if you look up table 3-23, there's actually a moment function already derived for this problem. So you can just plug and chug from it. And the other thing is, and we haven't talked about it until right now, but there is a table 3-1 in the manual that you can verify your answer with table 3-1. The purpose of this assignment is to just get comfortable with computing CB values, but you can also look it up in the manual. Okay, that's all I have, everybody. I will see you all on Friday. Hopefully my road's clear by then. We'll see you.